Yesterday, on the front, we talked about the basic derivatives, right? We looked at derivative of a constant, which basically derivative of a plain number is always 0. Derivative of a single variable, well, derivative is slope, right? So it is always 1. And then power rule is what we learned. So moving the power out front, multiplying by the power, and then decreasing the power in the exponent by 1. Now, today's general power rule. So basically, when there's other pieces, basically when there is a coefficient, which basically just means we're multiplying it by that, but general power rule, the derivative of the term a x of n, where a and n are real numbers. So yesterday we talked about bringing n down front and multiplying it. Well, basically all that we're saying is we're going to multiply n by whatever a value is already there. So when you bring your power out front to multiply, if there's already a number there, you multiply it by that power. Okay? So let's practice, and this will kind of review for today from yesterday. Y equals 3x squared. So we're going to find y prime. Okay. The way I think about this is I already have a 3 there, yes. And we're going to multiply by what power do we bring out front? 2. And then instead of x to the second, we're going to decrease by 1. So 2 minus 1, making the final answer here when we clean it up what? 6x. Easy enough? Very much what we were doing yesterday, just technically building one little step there. You're catching on. Derivatives, we always go down the power, right? Always, every time. Okay. I'm going to keep this moving. Stop me if I get going too fast or if you have questions, okay? S of t equals negative 5t cubed. So S prime of t, my brain says I already have the negative 5. I'm going to be multiplying by 3. T to the, instead of 3, it will be 3 minus 1. So S prime of t is what? Negative 15t squared, you got it? You're ahead of me? Okay, moving on then. What's the catch with C? Before you get started, this is what? 6x to the 1/2, correct? So y prime, there's a 6 out there. We're going to multiply by 1/2. X to the, what is 1/2 minus 1? Negative 1/2. So I have 3x to the negative 1/2. I would not leave a negative exponent. So I would write this in one of two ways. What are you guys thinking? 3 over, do you say x to the 1/2? Okay. 3 over x to the 1/2 is fine. What's the other option? 3 over square root of x. And I don't have one that is more correct than the other necessarily. They're both equally right. You need to understand the equivalency, right? That's the key there. So I can handle either or. Okay, before we start D, instead of it being 3 over x squared, we need to think of this as 3x to the negative second. So g prime of x, we already have 3 times negative 2, and then x to the negative 2 minus 1. What do we get here? Negative 6x to negative third. I would go one more step though, right? About negative 6 over x cubed. Not a cube root. It's x to the negative 3, not 1/3. Obviously, I caught a couple people there, didn't we? Saw a couple erasers happening.
No, I wrote a 3 instead of a 6.
Oh, okay. So you had a different mistake. Well, and we did just come off of a square root, so I can see the whole, I can see that mistake. I'm okay? I'm not going too fast? Stop me if I am, please, because... Okay, what do we know about this 4 over square root of x? It's 4x to the negative 1/2. That was my pitfall when I was doing this on my own. I kept forgetting the negatives and the exponents. It kept getting me in trouble. Okay. Negative 1/2 times the 4 that's already out there. And then x to the negative 1/2 minus 1. Negative half of 2, negative half of 4 is negative 2. X to the negative 3/2. Always just, negative 1/2 minus 2/2, right? I would not necessarily use a radical here, but again, get rid of the negative exponent. So negative 2 over x to the 3/2. And, okay, really check these algebra skills. This is negative 8 x to the, okay, good, negative 4/3, right? Review the exponent rules there. So, y prime, I'm going to be doing negative 4/3 times the negative 8 that's already there, x to the negative 4/3 minus 1. So I'm going to be subtracting 3/3, if you will, right? Let's see, negative 4/3 times negative 8. There's no simplifying there, is there? So 32/3 x to the negative 7/3. But I'm not going to leave it as negative 7/3. I'm going to take that to the denominator. So I'm going to say 32 over 3x to the 7/3. Are we catching on? Okay. Because basically, I mean, we're just going to keep building is what we're doing. Okay? So that's why I say, if I get to going too fast, please stop me. Okay. So the next step, we're basically doing what we've already been doing, except, okay, now we're going to talk about the sum or difference rule. And basically, the sum or difference rule says if you are adding individual terms, like pieces of a polynomial type thing, the derivative power rule that we're using, you just apply to each term. So if it's terms added, you just add the derivatives, basically. So official wording, the derivative of a sum or difference is the sum or difference of the derivatives. Okay, so if there's a derivative of pieces being added or subtracted, then your answer is going to be the pieces, adding or subtracting of the derivatives. Basic way to say, take the derivative of each term. Okay, shall we try it? So f of x is this equation. Derivative of x to the third. 3x to the second. Move the 3 out in front. Subtract 1 from the power. Makes it 3x to the second. I'm not going to show as many intermediate steps the farther we go, so I'll try and slow down some. Minus, that sign stays the same unless I have a reason to change it. There's already a 5, so derivative of 5x squared, 10x, because you're multiplying 2 by 5, which is 10. Subtract 1, we're at x to the first. Okay. Derivative of 2x.
2.
2. And again, I know we learned this rule. We learned the rule of just the derivative of, just a regular x to the first is just basically the number in front. But think about subtracting the power. If your x is a power of 1, when you do 1 minus 1, it's a power of 0. The x ceases to, exist. Each of my powers is decreasing by 1. The x ceases to exist. So a x term will always go to a constant. And what's the derivative of minus 7? 0. So I think there is no x, and so a constant then just disappears. There's no farther to go. So your answer is right here. Okay? So much better than definition of derivative. It really is once you get it all straightened out. Okay, B. Y prime equals derivative of 2/5 x to the 5th. I agree with 2x to the 4th, because 5 times 2/5 will be 2, and then x to the 4th. Plus derivative of x to the 4th. 4x to the 3rd. Move the 4 out front, subtract 1 from the power. Plus derivative of 3x squared. 6x minus derivative of 1. I'm not going to write my plus 0 or minus 0. Okay? Trying another one. Now, of course, got to throw the radicals back in, right? So I would maybe think about rewriting this before I start. The cube root of x is actually x to the 1/3 plus 5 square root of x is 5x to the 1/2. And if you can do that without the visual, more power to you. I kind of need to keep myself straight, honestly. Okay, g prime of x. Derivative of x to the 1/3. One-third comes out front. X to the negative 2/3. Because 1/3 minus 3/3. Plus derivative of 5x to the 1/2. Five over 2, because it's 1/2 times 5, so I would say 5/2. X to the negative 1/2. Okay, rewrite these. Put the get rid of the negative exponents by putting them in the denominator. So the first one, 1 over 3x to the 2/3. And this next one, I keep the 5 on top, take the 2 to the bottom, 2x to the 1/2. Are we okay? Okay. D. Before I get started on this next one, let me ask about 4 over x. What do you know about 4 over x? Yeah, that's really 4x to the negative 1 there, isn't it? Not that I should scribble out the original problem, but in my notes, I actually have it written beside it. So, okay. 5x to the 3/2. 3/2 times 5 is going to be 15/2. X to the 3/2 minus 1 is 1/2. Okay. Minus. Maybe I shouldn't be. Maybe I should be writing another step down here, but derivative of 6x to 5/3. So 6 times 5/3 is 30/3, which is 10. X to the 5/3 minus 3/3 is going to make it 2/3. I almost forgot about this next guy. Plus 4x the negative first derivative. Okay. -1 times 4 is -4, x to the -2. So I guess I am going to have to rewrite it for the last piece. So y prime 15/2 x to the 1/2 minus 10 x to the 2/3. And I would not say plus -4, obviously. I would say minus 4 over x squared. We've got E and F on the next page. Same type stuff. Let's see. Before I start this one, 3x squared is good at 3x squared. Minus, instead of 4 over x to the second, 4x to the -2nd. Instead of 2 square root of x, 2x to the 1/2. Again, rewrite it or don't, but. So, h prime of x. Trying to give you guys a moment to be ahead of me, because I know you guys prefer that probably. 3x squared. So 2 times 3 is 6. Subtract the power, so 6x. It's minus 4x to -2. But minus 4 times -2 is going to make it plus 8. X to the -2 minus 1 is -3. Plus 2x to the 1/2. So half of 2 is 1. X to the 1/2 minus 1 is -1/2. Not sure why I wrote that one coefficient of 1 in there, but I did. But it's also not my final answer, is it? So h prime of x, 6x plus 8 over x cubed plus 1 over x to the 1/2, or 1 over the square root of x. One more. Now, this is an important one to look at. So I remember seeing questions like this, like on AP multiple choice, and it always confuses people. It's really so easy. And there's a more difficult way we can go about it that we'll learn in 2-6, but all we know is how to do the derivatives of individual terms, right? So, do you see what you need to do, Maddie? Yeah, basically, this is a 3 terms up top divided by 1 top, right? Or 1 term on bottom. Divide each term by x. So rewrite the original problem before we get started. So the idea that, what's 8x to the 3rd divided by x? 8x squared. 4x squared divided by x? 4x. Minus 3 divided by x. Well, 3 divided by x is 3 over x. But for the purposes of derivatives, I need to write 3x to the -1. Okay, here we go then. Derivative of 8x squared. (16x). Derivative of 4x. What is the derivative of 4x? 4. Because when you take x to the first, you subtract a power, 1 minus 1 is 0. So that x is gone. So just 4. Minus, because we're always decreasing powers here, -1 times -3 is actually going to end up being plus 3. X to the -2nd when we subtract 1. So f prime of x is 16x plus 4 plus 3 over x squared. Obviously, the more you do these, the easier it'll be. Later on in the year, you won't be thinking a second thing about this type of derivative. Okay? It just takes practice. Are we okay with what we're doing? Okay. So as I said, what I've taught so far would have been maybe just 2 different lessons in my previous calc book. But this would be a different lesson. So this would be a 3rd different lesson. So now I think, do I have this on the next page? Is that the same thing? I do. Okay. It's just much bigger right here. Okay. So mixed in with learning the power rule. We're doing a lot of derivatives right now, guys. Okay. So we're going to start talking about derivatives of our trig functions. Okay. Each trig function has a specific derivative. Ultimately, best suggestion, it's a memorization game. Memorize them. Okay. Now, we will, and I think it's more in the next lesson, we will talk about how to derive them. So where if you forget what the derivative of cosecant is, you could use, what we know about cosecant to try and find it. But ultimately, best thing is to just memorize them. So, derivatives of sine, cosine, and tangent. Derivative of the sine function is cosine. So the derivative of sine x is cosine x. And I guess it doesn't say it here. The derivative of cosine is negative sine x. Okay, so you have to know that those two are each other, except the derivative of cosine is negative sine. And the derivative of tangent is secant squared. Maddie, the look on your face. Yes, it's just random, doesn't it? It appears to be random. Now, as you look at these graphs, okay, what is this first graph? You have in your notes, Miles. What is this first graph? I'm laughing as Miles back there trying to look over Jacob's hat. That would make me laugh. Okay, that is sine, yes? I think he was doing more as a funny thing, but it was, yeah. I say he does have this in his notes, technically, so. Okay, so realize this is sine x, right? I need you guys automatically recognize that as sine x. Sine starts at, well, it doesn't start, but when we think of just one cycle of sine, it goes through the origin, right? It has a period of 2 pi, or a cycle of 2 pi, max at pi over 2, pi, 3 pi over 2, 2 pi, right? Now, as we look at this, and actually I'm going to put this down here, basically what they're showing us here, this is our function graph. This over here is our derivative graph. What is this? This is cosine x, right? And so this is showing here that the derivative of sine x is cosine x. Now, think about some of the pieces we have looked at. The fact that, let's see, on sine, there's a min at pi over 2 and a max at 3 pi over 2. What do you notice in those spots at cosine? They're zeros, yes? Because sine has horizontal tangents, so slopes of zeros at that max and min. So here, they are zeros, right? As we look at sine, what's it start off doing first? The first thing it's doing is it's going up. It is increasing, yes? And then over here in the middle, it is decreasing. And at the end, it is increasing, right? Again, this is the whole idea of being able to draw the derivative function. Well, if a function is increasing, what kind of slope does it have? Has a positive slope. So over here where it's increasing, notice right here that it is positive in that it is above the x-axis. Okay? It's not that that has a positive slope, it's that that is positive as in is in above the x-axis. What about from pi over 2 to 3 pi over 2? That section is down below the x-axis, and because it has a negative value. Well, a decreasing function has a negative slope. And of course over here then, past 3 pi over 2, we're increasing on the sign, which means my derivative graph has positive y values and it's above the x-axis. So when I'm saying above and below, I'm talking in reference to the x-axis there. You see the connections there? Okay, because that's something we're going to work with. Now, grab your calculator just real quick. I'll be honest, I'd never done this before. It's not that I didn't realize you could, but I'd never done this. So, you can actually graph a derivative. Never thought of this, as I said, but you can enter the function as a function of x to be evaluated at the value of x instead of an actual number value. So, you know, Math 8 will give us derivative, right? Well, you can go into your y equals, and you can type, do your Math 8 there. You can type in the function you want, and then just instead of x equals a number, you're doing x equals x. And notice when you graph it, I don't know if this is worth me graphing here. Did you guys try it? I just thought it was interesting that if I go in while I'm in here, Math 8 gives me the derivative setup, d dx. If I'm doing of sine x, into your parentheses, then you just have to put x equals x. When I graph that, it should have changed my zoom settings, sorry. I'm going to do a zoom trig. Notice, I graph derivative of sine. What graph is it giving me? Cosine. And if you don't believe it, go down to y2 and type in cosine. Right? Are we in radians? No?
Yes.
I was just thinking about that, and I looked back to see Connor showing his calculator. I'm assuming your graph was not right. Okay, get in radians. And why does radians matter at this exact moment? It's a trig function, right? It's not that you have to have radians to graph a derivative. It's because it's the derivative of a trig function. Okay? So it's not that you always have to change to radians in here, but I did force it.
So is this like, are the increments on here the same as that?
If you do Z trig, it is. Yes. Which is Z7.
I just didn't know
Yeah, and that's what I like about Z trig is it gives us more, because if we just do a regular standard screen, it counts 1, 2, 3, 4, it counts up to 10, right? And so then like pi 3.14, like it's not right on value. That's why I like Z trig, because it puts it right on the value. Okay, so
like another graphic.
then you want to go back to a standard zoom if you're not doing something trig related. Okay. Okay, so just interesting information that you can graph the derivative of sine. And notice, derivative of sine, it provided a cosine graph, right? So, and of course there's the inspire thing, which we don't need to talk about. Okay. Not doing too bad. 2 more pages. I got this. Okay. So, I just talked about if we can't remember a derivative, we can always derive it. Now, this is not what we're going to do every time. However, you need to kind of see the process. You need to see how definition of derivative works here, because that's what we're going to use for this particular piece, is we're going to use definition of derivative and kind of show the connection there. So using the limit definition of the derivative, we can derive f prime of x for each of the following trig functions. You'll verify the derivative of the sine and cosine functions by using sum and difference formulas that we learned in pre-calc. Okay, we'll see about that one. So, excuse me. First of all, a little bit of information here. We talked about this already this year. The limit as h approaches 0 of sine h over h. Or think about those h's being x's is how we learned it. The limit as x approaches 0 of sine x over x. What is that? 1. Yes? Okay. That falls into one of those be familiar with it categories. At the same time, we also learned the limit as x approaches 0 of cosine x minus 1 over x, and that is 0. Okay, we learned those both together. Now, cosine of x plus h and sine of x plus h. This is the sum and difference formulas we learned in pre-calc that go like sine cosine plus cosine sine, or cosine cosine minus sine sine. This isn't sounding familiar, is it?
I don't remember what it's.
It like equals 1.
Oh.
No, it's just a way to, okay, if you have adding or subtracting here. So they were sum and difference formulas, because we had cosine, sine, tangent was a fraction, if I recall. Yeah, see, it's on the purple paper. Ethan still has the purple paper there by his side. So with cosine, cosine is the one that starts cosine cosine. And so cosine of x plus h is cosine x cosine h. Cosine is the one you change the middle sign, and so then it's going to be minus, and then we use sine sine. So sine of x, sine of h. That is one of our pre-calc identities that does randomly show its head. Okay? So sine of x plus h. This is the one that goes sine cosine, and then cosine sine, is that what we usually say, I think? So this one, it's sine of x, cosine of h. Keep the same sign, so it's plus, and then basically flip your variable with your trig functions. So cosine x, sine h. Right? We did these last year. Okay, so we're going to use that information here as we do these proofs, so to speak. Because that's what essentially what we're doing, is we're proving that the derivative of sine is cosine. So, derivative of sine x. My goal is to show that it's cosine. Well, other than memorizing the derivative, how can we find the derivative of sine? We can use the definition of derivative. Definition says the limit as h approaches 0 of sine of x plus h minus sine of x all divided by h. Yes?
Could we, like, that's just one voice to write derivative, right?
Yes.
So it's kind of the same thing as like y prime.
Yes. Okay, you're talking about my dy dx? Yes. There's one way to write derivative. Now, here's the deal. Well, I feel like in this situation, you would use a dy dx or a d over dx as opposed to y prime. Okay? And what I'm going to suggest is let's not avoid the dy dx's because they're different, because they will definitely show up. Okay? You'll see a lot of those. So, but yes, it's another way for derivative. Okay, guys, we've got to work with this. Limit as h approaches 0. Well, yeah, what did we just talk about? Sine of x plus h. Didn't I just write that out ahead of time? That's our sum and difference formula. So sine of x plus h can be rewritten as sine x cosine h plus cosine x sine h. We still have the minus sine x at the end and the divided by h on the bottom. And until we get rid of that h, we can't do this problem, right? Because we're dividing by 0. Now, trying to think, how did I do this? Okay, as we look at the top, we have two of the three pieces have something in common. And specifically, we're going to talk about the two pieces that have a sine x in common. So this piece and this piece have a sine x in common, yes? So I'm going to move those next to each other. I'm going to factor that sine x out. So the limit as h approaches 0. As I factor the sine x out, I'm going to have sine x of cosine h minus, and when I factor sine x away from itself, I'm left with a minus 1 into the parentheses. I still have a cosine x sine h term at the end, all over h. Now, I've set myself up to change this into two fractions, is what I've set myself up to do. Okay, and essentially we can think about it as two limits, but when I break one fraction into two fractions, the denominator has to go with both pieces, right? And I'm also going to break it up into two limits as I go. So, we're going to have the limit as h approaches 0 of sine x times cosine h minus 1 all over h plus, and now I'm going to do a second limit. The limit as h approaches 0, and this time it's of cosine x sine h all over h. Okay. We're set up to use our two special limits if you see it. You see it? Right here. Cosine h minus 1 over h. What's that limit go to? That goes to a 0. Over here, sine h over h goes to 1. Right? And that's that special limit over here. So, with that in mind, okay, so on this first one, it's the limit as h approaches 0 of sine x times this limit here. Well, the limit as h approaches 0 of sine x, we put 0 in for h. Sine x is just sine x. So officially, this first piece is going to be sine x times 0 plus my second piece, well, the limit as h approaches 0. Cosine x is just cosine x, because h approaching 0 isn't going to affect cosine x, times limit as sine h over h is going to be a 1. Well, sine x times 0 plus cosine x times 1 is all going to work out to be cosine x. So, what do I want to say here? I don't want to say that. I'm going to say dy dx of sine x equals cosine x. Okay? Now, is that something you have to be able to do on an everyday basis? No. But this is understanding definition of derivative, or trig derivatives, and all that. Yes?
You said that, like, when you split the two fractions that inside there are two small fractions, like, does the h not have to go into this sine x too?
No, because it's multiplying. And so if it's multiplying, like this is sine x times this, you could think of this as a 1, if you will, because you could think of it as a fraction times a fraction. Okay? Adding, yes. Multiplying, no. And so this one, you could also think of it being cosine x over 1, if that helps. Okay? Valid question. Anything else? Okay. Guess what? Same thing? Different function? Let's try it. Derivative of cosine is negative sine. Is that our goal? Is our goal to prove? So dy dx of cosine x. So in order to do the derivative of cosine, we're going to do the limit as h approaches 0. This time it's going to be cosine of x plus h minus cosine x all over h. Then, in order to do something with that cosine of x plus h, we're going to have to use that sum or difference thing, yes? So, limit as h approaches 0. Cosine is the one that goes cosine, cosine. So, cosine x, cosine h, change the middle sign to minus, and then it's sine x, sine h. Don't forget the minus cosine x all over the h. Okay. Again, we're looking for something in common that we can factor out of the two terms. It's going to work very similarly to last time. And my first and last term have a cosine x I can factor out. So the limit as h approaches 0. I'm going to factor out cosine x from my first and last term. So then I'm going to have cosine h minus 1. And then I still have minus sine x sine h all over h. And if you see where we're going this time, do you see I'm going to have a cosine h minus 1 over h? And over here on the second piece, I'm going to have a sine h over h, right? It's the same type idea of what happened last time. So the limit as h approaches 0, I'm going to break into two fractions. Cosine x, cosine h minus 1, all over h, minus the second limit as h approaches 0 of sine x, sine h over h. Cosine h minus 1 over h and sine h over h have their own little special things they go to, right? Cosine h minus 1 over h is going to go to 0. Sine h over h is going to go to 1. So, as I put 0 in for h, cosine x times 0 minus sine x times 1. 0 minus sine x. So the derivative of cosine x is negative sine x. Okay? So down here at the bottom, the derivative of sine x, or f prime of sine x, is cosine x. The derivative of cosine, or f prime of cosine x, is negative sine x. Okay? Oof, I gotta push, I guess. Man, I thought we were doing so good on time. That page took a bit. Okay. Moving along. Last set of new derivatives for today. Now, I will say tomorrow I don't think we learn any new derivatives, we just learn new rules. So, favorite derivative ever. The derivative of e to the x is e to the x. It's the one and only derivative that is itself. Okay, so the derivative of y equals e to the x has itself as its derivative. So if f of x equals e to the x, then f prime of x equals e to the x. Okay, easy enough. The other one we're learning, f of x equals, if f of x equals the natural log of x, then the derivative of the natural log of x is 1 over x. Okay, yes?
If it's f of x equals 0, doesn't that also have the derivative equals 0?
I guess.
Okay, she's pushing me.
I guess. If you want to get nitpicky, I don't know. I still, that one's, I don't know,
one's
that's
cooler.
different.
That one's cool.
Okay. I still like e to the x, e to the x. Okay. So now, here's the deal on these. Tomorrow, we learn things called quotient and product rules that would give us another way to do these. I'll be honest, when we put these in there, I had to go to the notes. I'm like, how do you do this without knowing tomorrow's lesson? But here's the piece I overread. Laws of logarithms. Okay, so we know the derivative of natural log of x. We just learned it, yes? We don't know the derivative of natural log of x cubed. What's the power rule of logs tell us we can rewrite this as? The power on a log can go out front. And now we have 3 natural log of x. Can I take the derivative of natural log of x with just a coefficient in front of it? Yes, because you just multiply that 3 in. And so what we're going to say here when we do the derivative, it's kind of like doing the derivative of x squared earlier. We kept the 3 and multiplied it by the 2x, right? So it's the same idea. We're going to keep this 3. What's the derivative of natural log of x? 1 over x. What is 3 times 1 over x? 3 over x. Okay. Another rule. Oh, yes.
What is that squared? Isn't it 3 lines squared?
Okay, but we're not doing, before we took our derivative, we moved the 3 out front.
Yeah.
And so we just have, we're treating this as 3 natural log of x instead. We're not doing the derivative of the x cubed, because I don't even know when chain rule comes up, because the derivative of something within a derivative would be chain rule, which that's actually got to be unit 3, because we don't even talk about that in this unit. So that's a whole other thing. So that's why we can't just say, okay, it's a derivative. Yeah, we can't. You don't know enough yet. That's the thing. And I know that's hard to explain. So, okay, so this one, I can't do a derivative of a log with there's 2 pieces in here. Yes? Do you see 2 pieces? I can't do that. That requires something called the product rule and the chain rule, and we don't know either of those yet. So, how can I rewrite this so it's just logs of individual things? I'm trying to think, what's it called? The product rule? Is it the product of logs? But basically, multiplication within a log can be rewritten as 2 logs being added. Is that what you said? So natural log of x squared plus natural log of e to the x. Don't take the derivatives yet, though. Move the powers. So when I move ln x squared and I move that power, it's going to be 2 natural log of x plus ln e to the x, move the power, it's x natural log of e. Yes?
So I get that it's ln x squared and then you write it as 2 ln x. Why is it on problem A, it's ln x to the third? Why is it ln 3 ln to the x? Shouldn't it be to the x squared? This is 3.
We're not doing a derivative.
Oh, okay.
This is before you get to calculus.
Okay.
We're not doing calculus right here. We're doing algebra.
Oh, okay. Never mind.
You're trying to overthink it. Same thing Connor was trying to do. We're not doing derivative. I'm using my property of log rules that we learned back in Algebra 2. Is that making a little more sense? I see where you're going with it. Okay, so same thing over here. Now I'm ready to start doing calculus. I haven't done any calculus yet. Now I'm ready to do calculus. Derivative of 2 natural log of x. Well, the 2 stays 2. What's the derivative of natural log of x? 1 over x, right? In a moment, I'll put that together. Plus, okay, guys, on this one, what is the natural log of e? 1. Natural log of e is 1. So what am I really taking the derivative of here? 1x. What's the derivative of 1x? 1. So g prime of x, 2 over x plus 1. This is obviously going to be the hardest part of the day. Questions there? Okay, so I think I have these next two on a different screen. Okay, so h of x, don't overthink it. Ln x is going to be ln x. What do you have to think about before you do the derivative of 1 over x? It's x to the negative 1, right? And that's going back to what we were doing earlier today. So, nothing fancy here. Do your derivative. Derivative of natural log of x is 1 over x. Now we're back to the power rule from earlier. Minus 1 times minus is going to make it plus x to the negative 1 minus 1, negative 2. Or h prime of x is 1 over x plus 1 over x squared. Okay. Division within a log can be rewritten as subtraction. It's a natural log of 2e to the x minus the natural log of 3x. Now, technically, if you catch it, there's still multiplication in both of these. This is 2 times e to the x. This is 3 times x. We can split them up again. And so we can split this up and say it's the natural log of 2 plus the natural log of e to the x. Now it's minus everything else, minus the natural log of 3. And actually, here, I'll do it this way. I'm using parentheses. It's minus the natural log of 3 plus natural log of x. Because you're subtracting that whole term, but it's multiplication within the term, so it's adding within the term, yes? We basically have 4 terms to take derivatives of here. Natural log of 2. What is natural log of 2? Is there a variable in it? Natural log of 2 is a number. I can plug that into my calculator, yes? What's the derivative of a number? 0, yes? You see what I'm saying there? Plus natural log of e to the x. Oh, I forgot to move my x out front, didn't I? But we already did that earlier. It was going to be 1, see above on that one, minus natural log of 3 is going to be 0. Derivative of natural log of x, that's going to be 1 over x. So you end up here with 1 minus 1 over x. We've got 2 more here. I mean, yes, they're like homework problems, but they're doable. When I put up the answer key, I've been putting up the notes key as well, yes? So you can grab them there. You can check with me if you have questions. Those are the only 2 I didn't get to. Homework kind of mixes everything up, guys, okay? It kind of mixes all the pieces together. You're going to have to really work to think about it. Equation of a tangent line, you're finding those slopes, those points. So work at it. I'll get the key up. Yeah, we didn't talk about, tangent line, but it's still stuff we're talking about. It's still derivative. It's still slope. So get the homework done for tomorrow.